Right.
Okay, welcome everyone after the coffee break, beer break, whichever, we don't judge. And so the second speaker of the day is Francois Thilmany from, oh God, I'm not going to pronounce this correctly, Leuven.
Sure.
And he'll be talking about uniform discreteness of arithmetic groups and the Lehmer conjecture.
Thanks, Michel. Thanks for the opportunity to speak. It's a pleasure to be online with you guys. And indeed, so today I want to say a few words about the connections between the theory of, let's say, linear groups in general and the famous Lehmer conjecture, which I'll introduce in my talk. And I'll be a bit more specific, and I'll talk about connections with, let's say, the theory of arithmetic groups, and then you'll see even more specific this question of uniform discreteness of arithmetic groups. So let's get into it. Let's see if I can switch slides. Does this work? Nice. Okay, so here's the plan for the talk. So I'll first introduce the things that are at stake, right? So I'll tell you a little bit about the structure of lattices in Lie groups and their arithmeticity. I think it's a good idea to have a short reminder. Then I'll introduce this question of what does it mean to be uniformly discrete for an arithmetic lattice, and yeah, how this relates to the Lehmer problem. And then in the last part, I'll talk about some other connections with my work with Lam Pham. So maybe I should say most of what I'm going to talk about. I mean, the original work that I'm going to present today is joint with Lam Pham from Brandeis, but I'll also talk a little bit about the work of a few other people in the last part, some other connections. All right, so here's the setup. So for this slide, G is a locally compact group, which I think everybody here likes. But later on, I'll be more specific, and G will always be the Archimedean points of some semisimple algebraic group defined over some number field, right? So if this is a bit abstract mumbo jumbo to you, you can think of something like SLN-R, SLN-C, things like this. So those are nice algebraic groups defined over Q in this case. And the R points are just SLN-R. So that's a fine locally compact. I mean, it's a Lie group. It's surely a fine locally compact group. So these are the guys I'm going to be looking at. I'm going to be looking at a bit broader family than just SLN, but you know, if you think about just SLN, you're already in good shape for understanding the talk. All right. So now, what's a lattice in G? A lattice in a locally compact group G is a discrete subgroup, such that if you look at the quotient, you can endow it with a regular finite G invariant, let's say on the left measure. So here the key property is finite. So the point is that the quotient G mod gamma has finite volume, and then gamma is called the lattice. So one time this can happen is if the quotient is compact. So if the quotient is compact, you can push down the Haar measure, and because it'll be, because the Haar measure is regular and the quotient is compact, the measure will be finite. So then you get the finiteness for free. And in this specific case, we actually call gamma uniform, so a uniform lattice or a cocompact lattice. This is not necessarily always the case. So there are non-uniform lattices, as we'll see in a little bit. So here's a silly example, which is the one I guess that gave the name to the concept. So Z to the n is a lattice in R to the n. So the discreteness is obvious, and the finiteness of the volume is also not too hard, right? The volume is this n torus, and with the standard Lebesgue measure, it has volume 1. I mean, it's even compact. So here you get it for free. Here's maybe a more Lie groupy example. So it turns out it's not obvious, but SLN-Z is a lattice in SLN-R. So the discreteness is, again, obvious for the same reason, just because Z is discrete in R. But the finiteness of the volume, that you have to work for a little bit. So that stems from what's called reduction theory. So you can show that you can find a nice fundamental domain, and then you have to compute the finiteness of the volume of that domain, but all of this is feasible. So you can show that this actually isn't a lattice. The quotient actually has finite volume, but the point is the quotient is not compact in this case. The main obstruction to compactness is, there's two ways to see it. It's either let's say it's unipotence. So the unipotents are the one that make it not compact. So Borel and Harishchandra, a bit more than 50 years ago, actually generalized this phenomenon, that SLN-Z is a lattice in SLN-R. So they were able to show that an analogous statement holds for a general Q algebraic group, let's say. So let G be such a group, and let's suppose for now it's a subgroup of SLN. So I give it to you as a algebraic Q subgroup of SLN. then if G has no Q characters, then the Z points of Z as defined here. So namely, do you see my mouse actually? Maybe this is a good question. Nice, great. So the Z points of G, which is just the intersection of the Q points of Z with the Z points of SLN. So that's well defined. And this is why I need the embedding in SLN. So these guys are a lattice in the real points of G. All right. So this condition is needed. If this doesn't hold, then it's not a lattice. It's actually if and only if. I don't need it, but yeah. And we even have a criterion to tell whether these Z points are a uniform lattice. This is this part, which is called Gaudemann's criterion, but it's actually, I think the full generality was first proven by Borel and Harishchandra in the same paper. So the Gaudemann's criterion says that this lattice is uniform precisely when G has no Q co-characters. So maybe I should tell you what a Q character is, right? And a Q co-character. So a Q character is just a map from the algebraic group G to the multiplicative group of, in this case, Q, because the group is defined over Q. And the co-character is the dual. So it's a map of the multiplicative group of Q into the algebraic group. So for example, in the case of SLNR, look, let's say it's defined over Q. So in the case of SLNQ, you can clearly embed the multiplicative group of Q in SLN. Let's say, you put it in the two first entries, A inverse, and then ones on the diagonal, something like this. So this also, confirms that this lattice was indeed not uniform. But the theorem also applies to SLN because obviously SLN has no Q characters. The reason is it's a simple Lie group. So if it had a Q character, what would be the kernel, right? It doesn't have normal subgroups. All right. So let's see, let me switch. Yeah, so as I pointed out, so it applies to simple, but in fact, it applies in general to semi-simple groups for free. So there you don't have to check. I mean, the assumption on characters comes for free. And there's also a version for arbitrary number field. So here I stated it over Q, but you can actually replace Q by a number field. And then you just have to be a little bit careful. You have to replace Z by the ring of integers of that number field. And you have to make sure that the embedding is nicely defined over that number field. But it applies pretty much the same. Now, this fact that all these Z points of algebraic groups are lattices probably points to the fact that these objects are interesting to study. And as such, we'll give them a name, right? So any lattice that's commensurable to this construction I just did. So I take a group G, I embed it in SLN, and then I intersect it with SLNZ, right? Any lattice commensurable in G, commensurable to such a subgroup will be called arithmetic, right? And this I can do for any embedding. So you have a variety of arithmetic subgroups that change if you change the way you get them as an embedding in SLN. And I need to, so for practical purposes, the right definition to work is not quite this, so I need to extend it a little bit. I also need to include images and things commensurable to images of such lattices by morphisms, which are, so epimorphism, what I mean by this is in the category of algebraic group, but you can think about a surjective morphism, it's not a big deal, or let's say like finite index image or something like that. It doesn't matter too much. With compact kernel, that's the important part. So if I have a group G, I embed it in SLN, I intersect it with SLNZ, I get an arithmetic lattice. If I quotient by a compact subgroup of G, the image will be an arithmetic lattice. And if I get something commensurable to this, I will also call this an arithmetic subgroup, all right? So this way, arithmetic subgroups are closed under commensurability and taking compact quotients by compact subgroups. So this is important, you'll see later, this is the right definition anyways. Let me give a few more examples now that we have this theorem of Borel and Harishchandra. So I'll give you two more examples of arithmetic lattices, but this time in a bit more complicated groups. So if you apply this theorem to Q adjoint square root of 2, there the ring of integers is just Z square root of 2. You get for free that I didn't tell you yet what I have to put so maybe I go back to this. In this version, if you replace Q by number field, right? Z changes and becomes a ring of integers, but I also need to tell you what happens with R. So what happens with R is you take the product of all the Archimedean completions of your number field, right? So it's K tensor R if you want. So you have to have all the Archimedean completions. So Q has only one, that's why here I only have one R factor. So with this in mind, you realize that what you have to put here is the SLN points of q square root of 2 tensor r, and that's just 2 copies of r, right? Because square root of 2 is a real number. I mean, yeah, 2 has a real square root, so the tensor product splits. You get 2 copies of r, and you have to know also how this embeds, and it embeds. So this embeds not diagonally, but almost diagonally. You just have to use these 2 different embeddings of q square root of 2 into r, which send respectively square root of 2 to the positive square root of 2 and negative square root of 2. Now, here's a bit more complicated example. Now, instead of giving you just SLN, I'm going to give you a unitary group. So here's the field. K is against q square root of 2. Now, L is, I adjoin a further square root of 2. And I give you this Hermitian form. So it's just a standard, diagonal with coefficients 1 Hermitian form. And I define G to be the special unitary group that preserves this Hermitian form. So in this case, I can also apply Borel and Harish-Chandra's theorem. And what I get is that the z square root of 2 points of G are a lattice in, again, this product of the 2 completions. So now we're going to look at a little bit that the embeddings are the same as before. Now we're going to look at a little bit at what these 2 completions look like. So the first one, so in the first embedding, I send square root of 2 to the positive square root of 2, right? So in particular, if I want to take a further square root of 2, right? If I want to construct L from there, I can already do it in R, right? Because I mean, square root of 2 is a positive number, so I can take a square root in R. And this shows that actually this completion K sigma 0 contains L. And because it contains L, which is the field that defines the unitary, the Hermitian form, this is general Hermitian form theory, then the group actually splits and you get back a copy of SLN. So this is how I get this SL2. I mean, I said SLN, everything is SL2, I guess, because I only give you 2 variables. Yeah, so you get just a copy of SL2R for the first embedding. And for the second embedding, what happens now is that square root of 2 gets sent to minus square root of 2. And there you can't take another square root for free in R. And in fact, instead, what happens is that the extension of L to K sigma 1 is just a complex numbers. And this Hermitian form just becomes the standard Hermitian form of C over R. So the group you get is actually just a standard special unitary group, SU2 of R. And this we know is compact. So you have a product of 2 groups. The first one is SL2R, and the second one is a compact group. So in particular, you see me coming. I can mod out by the compact factor, and the image will still be, by my definition, an arithmetic group. So the projection of this G Z square root of 2 onto the first factor, which is just SL2, is an arithmetic lattice in SL2R. Now, I have a question for you. I don't know if you've been paying attention. Is this lattice uniform or not? What do you think? So remember, we have a criterion, right? I don't know if anybody wants to make a guess. Nope. All right. So we have a criterion, right? The criterion says we have to look if there is co-characters defined over, in this case, the number field in G. But if there were such co-characters, right? So if G had K co-characters, then in particular, if I base change to sigma 1, right? If I look at the second embedding, the base change of these characters these co-characters will be co-characters of K sigma 1 in, oh, what happened? Huh. Yeah, sorry, something happened to my screen. I think nothing happened to the stream. Anyways, so what I was saying is that if you base change these co-characters, you'll get co-characters from K sigma 1 into G, right? K sigma 1 is just R, so that's no big deal. But the point is that G over K sigma 1 is compact. And you cannot have a co-character into a compact group because the torus, like the multiplicative group, is not compact. So you'd have, like, you look at this image and you'd have ways to contradict the compactness of, in this case, G over K sigma 1. All right. Another way to put it, if you know a little bit of algebraic groups, is K sigma 1 is compact if and only if it's anisotropic, which is exactly the same thing as saying it has no co-characters. And if I have a co-character over K, I can base change it to a co-character to K sigma 1, and that's a problem. All right. So in particular, I can't have co-characters over K. And in particular, this is where I want to get to. This lattice has to be co-compact. So the quotient is actually compact. So this is what I've written here. And this also shows that this lattice is a new lattice. So right now, I only gave you one example of a lattice in SL2R. I gave you SL2Z on the previous slide. This is another example, and it's a genuinely new example in the sense that it's not commensurable And it's also not the image of the other one. They're not images of each other using compact kernels and commensurability, because this would preserve cocompactness. Like the image of a cocompact lattice would be a cocompact lattice, and anything commensurable to it would be as well. All right. So any questions about this? So all you have to remember from this is there is this way of constructing arithmetic lattices. This will come up later. And you see that there is a little bit of, how do you say it? The variety comes from these embeddings, right? If you take the stupid embedding of SLN into SLN, then you just get the Z points and you get, you know, the standard non-uniform lattice. But here, if you play around with the number theory a little bit, if you play around with this embedding, with what the shape of the group, of the form of the group of over your number field is, you also change, if you change the number field, it actually also changes the lattice. So I could have taken, instead of K, I could have added a square root of 3 instead of square root of 2, and I would get another lattice. You need other arguments to show that it's different, but the point is that you have a variety of lattices which comes with this variety of the construction. All right, let's keep going. So Margulis, I think in the 70s, around 75, yes, somewhere in the 70s, proved a very impressive converse to this Borel and Hysandra theorem. So he showed the following. So he actually showed that if I give you let's say a simple R group of real rank at least 2, so this is a crucial hypothesis, and then I give you an irreducible, I mean, if the group is simple, I don't need it. I just give you a lattice in GR, then this lattice is actually arithmetic. So actually in higher rank real Lie groups, all the lattices are arithmetic. So they all come from Borel-Harish-Chandra construction plus this commensurability and compact quotients. So this is quite impressive. And the nice thing about this is now, if I give you a lattice in one of these groups, you know that there is a construction that looks like the one I presented on the previous slides that gives you the lattice. So there exists a group, there exists a number field over which this group is defined, an embedding into SLN that gives you the points, and then maybe a compact kernel that in such a way that your lattice is just commensurable to the image of the Z points. This is the punchline. All right. So as a consequence of this very nice theorem, Margulis was able to deduce the following statement, which is a bit reminiscent to the Kazhdan-Margulis theorem. I don't know if you are familiar with this. So Kazhdan-Margulis says that if you, let's say I give you a simple Lie group, there exists a neighborhood of the identity such that every lattice I give you has a conjugate which doesn't intersect this neighborhood non-trivially. So it's a neighborhood that doesn't avoid all lattices, but if I give you a lattice, it at least avoids one of its conjugates, except obviously for the identity. All right, so the statement that I want to talk about now is a bit similar, but it's not quite the same. Is the following. So I give you again a semisimple R group. Then there actually exists a neighborhood of the identity in GR such that for every non-uniform irreducible arithmetic lattice, so this arithmeticity assumption is for free if the rank is bigger than 2, the intersection of gamma with this neighborhood contains only unipotent elements. So the difference with Kazhdan-Margulis is now you may have something in the intersection, you may have some unipotent elements, it's not necessarily trivial anymore, but you don't have to take a conjugate. This neighborhood is uniform for all lattices gamma that satisfy the assumptions of the theorem, right? So this is what I mean by a statement about uniform discreteness. So it's of lattices. So it's something like I give you a neighborhood of, there exists a neighborhood of the identity such that it avoids in some way uniformly all lattices in the group. So maybe we can prove this. Actually, it's not too bad if you have the arithmeticity theorem in hand. So I'm going to use the arithmeticity theorem to write gamma. So we know that gamma is commensurable to the image of the Z points of some group by some morphism with compact kernel. Right? This is just a definition of an arithmetic subgroup. And I'm telling you that for simplicity, we may as well assume that H is just Q simple. So we may assume H is defined over Q. It's a simple algebraic group. And what I'm going to do now is I'm going to deduce that the kernel of this map, so the kernel is compact, but I'm actually telling you that it's finite. So the reason why is similar to something we've seen before. So if this wasn't finite, then there would be a compact part, right? A non-trivial compact part in H. And this would force H to be Q anisotropic, right? That non-trivial, so that positive dimension compact part would prohibits H from having Q co-characters for exactly the same reason as before, because it's supposed to be a compact part and that can't happen. If H is Q anisotropic, then by Gaudemond's criterion, the lattice would be uniform. But by the assumption of the theorem, I have a non-uniform lattice, right? So because I have a non-uniform lattice, I cannot actually have compact kernels. So in this case, you get genuinely just commensurability. Oh, I mean, you have a finite kernel. Who cares about that? So in particular, another way to phrase this is that tau is an isogeny. It's exactly the same thing. So it's saying that it has finite kernel. All right. So if tau is an isogeny, then we have an isomorphism between these two Lie algebras, right? The Lie algebra of H is isomorphic to the Lie algebra of G over, let's say, I mean, G is not defined over Q, so let's say over R. And by construction, because this is the Z points, the image by the adjoint map of HZ preserves a lattice in this Lie algebra. So this is the analogous thing as SLN-Z preserves the lattice of integer matrices in the Lie algebra of SLN. It's nothing more than that. But because the Lie algebras are isomorphic and my gamma is commensurable to HZ, I mean to the image of HZ, then I can actually get the same thing in G. So I actually have that the image under the adjoint action of gamma preserves a lattice in G, in the Lie algebra of G. So now let me take a basis of the Lie algebra of G for which the elements of add gamma have all integer entries. So this is what I wrote over here. In this basis, you can compute the characteristic polynomial of these guys, right? So this immediately implies that the characteristic polynomial of all the add gammas for every gamma in my lattice have integer coefficients. So that's quite nice. It gives you strong information about the elements of my lattice. And in particular, it allows me to immediately write down a neighborhood that will avoid everything but unipotent elements. So here's the neighborhood. I just asked that so the neighborhood consists of elements G in G such that the characteristic polynomial of their adjoint is 1/2 close to the following polynomial. So here's a polynomial of degree dimension of G, right? X minus 1 to the dimension of G. And I ask that every coefficient of the characteristic polynomial of add G is not further away than 1/2 of the corresponding coefficient in this polynomial that I wrote down. So in particular, if you have an element in gamma that's in U, right? Its characteristic polynomial has integer coefficients, and it's 1/2 close to another polynomial with integer coefficients. So these polynomials have to be the same, right? So the characteristic polynomial of any element gamma that's in this neighborhood is x minus 1 to the dimension of G. But if the characteristic polynomial of my gamma is this, I mean, this is exactly saying that gamma is unipotent, right? Well, I guess I'm done. So I didn't write it down, but yeah, so this concludes the proof. Any gamma that lies in this neighborhood will be unipotent, and this is exactly what we have to prove. This is exactly the statement of Margulis' theorem. All right, any questions about this? All right, let me move on then. So the immediate question is, what happens with uniform lattices, right? Here we had non-uniform lattices. We saw that this was kind of necessary in the proof to get the isomorphism between the Lie algebras. Can we do the same thing? Maybe can we push it for the uniform case? So this would be the kind of statement you'd expect if you wanted to do this. So this was conjectured by Margulis probably exactly at the same time as he proved the previous theorem. And it says the following. So if I give you a semisimple R group, there exists a neighborhood of the identity such that for any uniform, this time, irreducible arithmetic lattice, the intersection of any such lattice with U contains only torsion elements. So this is again a statement of uniform discreteness where the neighborhood doesn't depend on the lattice. And this time the right flexibility is torsion elements. So it's a general fact that kind of comes from what I've talked before, that uniform lattices don't have unipotent elements. I've briefly mentioned this before. So here you don't expect the statement to be the same as the previous one. The right thing to put instead of unipotent is torsion. This is the right thing to put there. So let's try to see if we can prove it, right? So we'll just do the same thing. So I use arithmeticity. I know gamma is commensurable to the image of the z points of some group by some morphism with compact kernel. And I again can assume that H is Q simple. This is no restriction. But the problem is this time, my kernel is not finite. It can be a non-trivial compact group. And hence, so I still get that there's some lattice preserved. I still get that something is integral. Namely, I get that the action of the adjoint action of hz on the Lie algebra of H, that one is nice. That's an integral action. But the problem is this Lie algebra splits into Lie G plus Lie of the compact kernel. And the compact kernel is now non-trivial, and we have to deal with it. So this is the issue. So in particular, if you restrict it to just the G part, you don't have integer coefficients anymore. You have integer coefficients on the direct sum, but this does not imply that. So the characteristic polynomial will split as a product, right? The G part and the K part. And if you split an integral polynomial in the product of two, it's not necessarily the case that that one of them has integral coefficients. But at least we have, so this is exactly what I said. So at least we have that it splits as a product, and the product is it's a factor in this product, and the product has integer coefficients. And the question that remains is to control the part that we don't really understand. So this new compact kernel that's non-trivial, this is what we have to control. All right. So the piece that we need to control this is precisely Lehmer's conjecture, actually. So if you've heard of Lehmer's conjecture, you can probably see it coming. Otherwise, I'll introduce it in a couple few slides. So let me just tell you what the Mahler measure is first. So if I give you a polynomial with, let's say, complex coefficients, and I write it like this, so I write it as a product of its roots times the leading coefficient, then the Mahler measure of P is simply defined as the leading coefficient times the product of all the roots, of the modulus of all the roots which are bigger than 1. So I take all the roots which have modulus bigger than 1, and I take the product of all these moduli. So that's the Mahler measure. In my case, all the polynomials will be monic. So, you can even forget about C. It's just the product of all the roots that are outside the unit disk, basically. If alpha is an algebraic integer, then I name P alpha its minimal polynomial, and I define the Mahler measure of alpha just to be the Mahler measure of its minimal polynomial. So nothing, just a convention here. Two properties. So this measure is obviously multiplicative. That's extremely easy from the definition I gave. There's other definitions where this may be less obvious, but here it's completely obvious. And we also know what happens when the Mahler measure is 1. So what happens if the Mahler measure is 1? Then alpha has all its, so if here alpha is an algebraic integer, right? So if I give you an algebraic integer whose Mahler measure is 1, then this means that all its Galois conjugates are inside the unit disk, and it's a theorem of Kronecker that actually, in that case, alpha is a root of unity, and in particular, they're actually all in the unit circle. There's nothing in the unit disk. All right, and so the converse is quite obvious. If you have a root of unity, of course, it's on the unit circle. All the norms are 1, and the Mahler measure is obviously 1. All right. So now I can state the Lehmer's problem. So he initially stated as a problem. I read as a conjecture just because it's convenient for me. But he asked whether this was the case. I don't think he had enough data to make an actual guess. So the question is the following: does there exist a gap epsilon such that for any algebraic integer I give you, either the Mahler measure of alpha is 1 and alpha is a root of unity, or the Mahler measure of alpha is bigger than 1 plus my gap? So this is the question. It's conjectured that there is such a gap. So it's conjectured that there exists an epsilon such that every Mahler measure is either 1 or at least 1 plus epsilon. So this is exactly the missing ingredient to complete the proof. I'm using a conjecture to prove something. So whatever I'm going to prove just will remain a conjecture. But if we knew this, if we knew the answer to Lehmer's problem, then we could conclude the proof that I wanted to do on the page before. So here's how it goes. So the problem was this compact kernel K, right? But now I can control it. So I do exactly what I've done before, right? So I write H as a sum of, the Lie algebra of H as a sum of the algebra of G and the algebra of the compact part. I write the characteristic polynomials like this. I factor them. I know that the product is in Z, right? But I also know that because K is compact, all the roots of the characteristic polynomial of the K part have to be, so I write roots of 1. Really, they have to be on the unit circle. They have to have norm 1. This is maybe an abuse. It doesn't matter. So all we need is that they're on the unit circle. If they're not on the unit circle, you have a problem. You can't have this in a compact group, in a compact Lie group. So in particular, because all the roots of this guy have norm 1, the Mahler measure of this part of the polynomial, which doesn't have integer coefficients necessary, right? This is important, but you can still define the Mahler measure, and the Mahler measure is still multiplicative, you know, over C. This Mahler measure will be just 1 because all the roots of this polynomial are on the unit circle. So in particular, the Mahler measure of the first part is equal to the Mahler measure of just the characteristic polynomial over G. So this last guy doesn't come up in the Mahler measure. It comes up, so it messes up the integrality of pH, but it doesn't mess up its Mahler measure. So now that's what I'm going to use to define the neighborhood. So by the Lehmer conjecture, or by the solution of the to the Lehmer problem, so I have what I said, right? PG, the Mahler measure of PG is the Mahler measure of pH, and this this Mahler measure is at least 1 plus epsilon if it's not 1, because pH has integer coefficients, right? pH is the product of, that's the thing we control. The part that we didn't control was pK. So in particular, if if pH is bigger than 1 plus epsilon, PG is as well. And what happens if it happens to be 1? If it happens to be 1, then PG is also 1. And then actually gamma is torsion. So why is that? Maybe this is because then the pH is Mahler measure 1. So that's an integral polynomial. So that guy, all its roots are roots of unity. And now PG is just a factor of pH. So all its roots also have to be roots of unity. And if your eigenvalues are all roots of unity, and you're in a cocompact lattice, which has no unipotence, then you're necessarily torsion. So this is kind of the argument. So that's nice, right? So this is what you want. So if the Mahler measure is 1, I have a torsion element, which is exactly the exception I allowed in my neighborhood in the statement of the theorem. And if it's not, there is this gap. So I can define this neighborhood, right? I can define the following neighborhood of the identity. I just ask that the Mahler measure of the characteristic polynomial of the adjoints of my elements is less than 1 plus epsilon. So this is I use this gap to make a neighborhood that will exactly avoid my elements from the lattice, except if they're torsion. So this is does it make sense? So of course, if an element of gamma is in U, then it has Mahler measure less than 1 plus epsilon, and by the argument above, it has to be 1, hence it has to be torsion. This is the thing, because by the Lehmer problem, if you have integer coefficients, you have to respect the gap. Either you're above 1 plus epsilon, or you're exactly 1 and all your roots are roots of unity. All right. So now, of course, we don't know yet the answer to the Lehmer problem, but it's quite interesting to see how it pops up, right? Because this is exactly, at least looking at the proof, this seems like exactly the tool we're missing in this case. This is exactly what you need to control the compact kernel. And I'll say a little bit about this later on. So if you paid attention closely, we could have even been more, how do you say it? We could have even made some savings. Everything in the argument had bounded degree, right? So the dimension of G was fixed. And so the part, if I go back to, yeah. So this part had always bounded degree. And all the roots of my polynomial pH, which were outside the unit disk, were roots of PG. Remember, because PK was a polynomial associated to a compact group, and there all the roots were on the circle. So in fact, the only thing we used is the following, weaker version of the Lehmer conjecture, which I call the Lehmer conjecture at the level dimension G. It's the following statement. So before writing the statement, just a definition. So this S of alpha just counts the number of roots of the minimal polynomial of alpha of norm greater than 1. So this is exactly the number of non-trivial factors in the definition of the Mahler measures. So with this S in mind, here's a weaker statement. So instead of having a uniform gap for all algebraic integers, I allow the gap in Lehmer's conjecture to depend on S. So if I give you an algebraic integer alpha, I count the number of conjugates alpha has outside the unit disk. And depending on this number, I have a gap. So the epsilon, the gap, that may depend on the number, but not on anything else. So any algebraic number that has less than S roots outside the disk should have the same gap epsilon in the statement of the conjecture. And this is exactly what we've used, because in our case, the only thing we cared about was, we knew that it was bounded, S was basically bounded by the dimension of G. This is what I'm saying. If you plug in s equals to 1 in this weak Lehmer conjecture, then what happens is you're looking at algebraic integers which have exactly one conjugate outside the disk. So this conjugate has to be on the real line, because otherwise by complex conjugation you have two. And then you actually, then you realize that you're just landed yourself with the definition of a Salem number. So a Salem number is literally one that has exactly one Galois conjugate on the real line outside the unit disk. And so in this case, in the case s equal to 1, you just get this conjecture. This is also a famous conjecture about Salem numbers, which would also follow. So this follows from the weak Lehmer conjecture, which itself follows from the full Lehmer conjecture. And this is also something that people have studied in number theory. All right. All right. So briefly, I can cover. So now you can ask what's known. What do we actually know about the Lehmer conjecture? Is there reason to believe that it's true? There is good reasons to believe that it's true, although we're far from it. So here's something that's known. So it's known that if you want to approach 1 using the Mahler measure, you have to have the degree of your polynomial go up. So this is known. So if there's a counterexample, namely if there is a sequence of polynomials whose Mahler measure goes to 1, these degrees have to go up, and they have to go up this fast. And there's also something else that's known. It's also known that if there is a counterexample to the conjecture, then eventually in this sequence of Mahler measure that goes to 1, eventually the polynomials have to be palindromic. So this is because if you have a monic non-cyclotomic polynomial that has Mahler measure smaller than the Mahler measure of this specific polynomial, then your polynomial P is actually palindromic. So note that this one is not palindromic. So in particular, this guy has the smallest Mahler measure among all non-palindromic polynomials. So it's and here's the smallest Mahler measure we know is the Mahler measure of this palindromic polynomial. And ironically, surprisingly, this was already, this polynomial was already known by Lehmer. I think, in fact, he discovered it. I think he wrote down this polynomial for the first time. He made a bunch of computations, and this is the one that he found that had the smallest Mahler measure. And so without a computer, obviously, this was in 1933. And now we haven't found better. Even, I don't know how far people have looked with the computer. I'm not an expert in this, but yeah, it's quite surprising. So yeah, there's a bit of arguments to believe that this conjecture may hold. Okay, so now let's talk about some things that are related to this, right? So now I want to draw some connections with a few other topics, connections of the Lehmer conjecture with a few other topics. So we've seen one already, right? Namely, we've seen that if we knew, let's say, the Lehmer conjecture or this weaker version that I talked about, then we can deduce uniform discreteness of cocompact lattices. We didn't need it for non-cocompact. This we could get away with without. Here's another connection. So it's been conjectured in geometry that there exists a lower bound for the length of closed geodesics in all arithmetic hyperbolic surfaces. So there's a uniform lower bound on the length of closed geodesics in these arithmetic hyperbolic two-manifold surfaces. And Newman and Reed, and independently Suri, they have actually shown that this short geodesic conjecture, namely, the existence of a gap under the length of the closed geodesics, is actually equivalent to the Salem number conjecture that I introduced before. So the Salem number conjecture was the weak Lehmer conjecture for s equal 1. Is the easiest case, if you want, of the Lehmer conjecture, where you look at polynomials with only one root outside of the unit disk. In that case, the Mahler measure only has one factor. So there's a version of this conjecture for manifolds of dimension 3. So in that case, you have arithmetic hyperbolic 3 manifolds. And in that case, you also get a statement like this, where this conjecture would be equivalent to a complex Salem number conjecture, where so it's not a gap for the Mahler measure of Salem numbers, it's a gap for the Mahler measure of algebraic integers, which have exactly two Galois conjugates outside the disk, and these two are complex conjugates. So they're like kind of they're the complex version of Salem numbers. Instead of being real, they're complex, but there's only one root outside the disk. we can actually extend. So this is what Lam and I have done. So we can actually extend this theorem of Surrey and Newman and Reed to general locally symmetric spaces, not just hyperbolic 2 manifolds and 3 manifolds. And the full statement you get if you do this is the following. So you can actually show that the weak Lehmer conjecture that we've used to prove Margulis' conjecture is actually equivalent to it. And more precisely, if you know Margulis' conjecture, so the one about uniform discreteness of cocompact lattices, right? There exists a neighborhood such that every cocompact lattice intersects it only in torsion elements. So this conjecture for groups of dimension less than 3s gives you Lehmer's conjecture at level s, which in turn, and this is the implication we've seen, gives you Margulis' conjecture for groups of dimensions smaller than s. So this last implication is exactly what I've proved a few slides ago. So that's where we saw that the Lehmer conjecture was exactly the missing piece to conclude this, to deduce this conjecture of Margulis. All right, maybe I can skip this actually. So I have a few elements of the proof, but I think for the sake of time, it's maybe better to move on. I can come back to this if people are interested. Does this work? Nope. All right. So for the last topic, I'll talk about something different now. So we're done with arithmetic lattices. Instead, I'll talk about just general linear groups, so general subgroups of GLN. So let gamma be just an abstract group, and S be a subgroup of gamma that's, a subset. S be a subset of gamma that's symmetric. So I didn't write it, but I may as well assume that one is it doesn't matter. So the exponential growth rate of this subset in gamma is just this quantity here that I wrote. So it's you compute so Sn, S to the power n. So this thing here is everything in gamma you can obtain as wards of length at most n with letters in S, right? So you multiply S with itself n times. You get a subset of gamma. Then you compute the size of that subset, and you take an nth root, right? So if you take the limit of this quantity as S going to infinity, what you get is precisely the asymptotic exponential growth rate of S in gamma. So if S has exponential growth rate, the quantity here you expect is precisely the exponent in the exponential growth rate. The only reason why the limit is there is because we know that, this may not be achieved immediately. It's asymptotical. All right. And we're going to say that this group gamma has uniform exponential growth. If you have a lower bound, right? So gamma has exponential growth with S precisely when this quantity is bigger than 1 for some fixed S. So if you give me a fixed S, it will grow, the set S to the n will grow exponentially precisely when this quantity is strictly bigger than 1. And I will say it's uniform, so the exponential growth is uniform, if this is actually uniformly greater than 1, in the sense that the infimum for all subsets, all finite subsets that generate gamma of this quantity of this growth rate is actually bigger than 1, right? So then I say gamma has uniform exponential growth. Here's a short fact. So whenever they have exponential growth, it's not necessarily the case always, but when they do, it's known that linear groups, solvable groups, hyperbolic groups, all these groups automatically have uniform exponential growth. So if they have exponential growth, there's actually a uniform gap on the growth rate. Breuillard, I think, conjectured the following for linear groups. He conjectured that for any D, which is the size of my matrices, which I will allow, there exists an epsilon depending on D, such that for any field, so the D does not depend on the field, and any subset S, the D also doesn't depend on the subset of GLDK, right? So this D fixes the size of the matrices, but I'm free to choose the field. This is important. So anytime you have such a subset S that generates a non-virtually nilpotent group, then you have the epsilon gap in the growth rate. So then the exponential growth rate of S is bigger than 1 plus this gap that depends on D. Right, so this means basically, in short words, there is a uniform gap in the exponential growth rates of linear groups with bounded size on the matrices, but no algebraic entry. I mean, algebraic entries, algebraic in the sense that there are entries in the field, but no condition on the field, right? So there's the only constraint is you have to bound the sizes of the matrices, but you can change the field. So there's actually it's a strong statement. And the existence, so the existence of groups with sub-exponential growth, so their existence, from that you can deduce that actually you cannot ask for a stronger statement. So you cannot ask that epsilon be independent of D. So you can't ask for a uniform gap across all linear groups regardless of the size of matrices, because it's known that this epsilon has to go to 0. Yeah, so you can construct examples of which the growth rate goes to 1. So epsilon goes to 0 using these groups of using, I don't know, linear quotients of these groups with sub-exponential growth. All right, so this is kind of the strongest you can hope. So here I just copied what I said on the slide before. And what I want to get to is the following theorem of Breuil. He actually showed that this conjecture of uniform growth, but just for, so now if I restrict in the conjecture, not any non-virtually nilpotent group, but instead I restrict to, what do I want to say? Yeah, right. So if I restrict this conjecture not to an arbitrary non-virtually nilpotent group, but just let's say to a meta-abelian or maybe just a solvable one, that actually already implies the Lehmer conjecture. So this shows that this conjecture is reasonably strong. And I think, yeah, so somebody mentioned, but I've never looked for a reference. I think Breuil actually showed that it's an if and only if. I think he also showed the converse, but this I would have to look up to make sure that I'm not saying something wrong. And he also showed, so Breuil also showed using his uniform Tits alternative that actually this conjecture holds for the non-virtually solvable groups, right? So here there's there's different regimes, right? So if it's nilpotent, then you don't have exponential growth, so you can forget about those. If it's not virtually solvable, then you get uniform exponential growth with, the right dependency on the epsilon, just using another argument, so namely the uniform Tits alternative of Breuil. And then the regime in between these, let's say solvable, I mean, the baby case is meta-abelian, but let's say the solvable case, if you could pin that down, so if you can show that for those guys, you have uniform exponential growth, then you can deduce the Lehmer conjecture. And as I said, I think the converse is also true. Yeah, so this is kind of what I wanted to talk about today. So it's and it goes a bit all directions, but all I wanted to convey is that there is these a bit surprising at first connections, with this statement, this big conjecture in number theory that if I gave you the conjecture like this, nobody would ever care about it unless you're a number theorist. It's complicated. It's about algebraic integers, and you don't see what the point is. Kind of like the Riemann hypothesis. I mean, maybe that's not a good example, but the similar feeling. You see it and you're like, okay, this again, right? But then if you present it this way, so you ask questions about linear groups, which now everybody here cares about, and you see that the tool that's missing is precisely this statement about number theory. So in the beginning, it's arithmetic lattices. You could say I'm cheating. I'm already hiding the number theory and the arithmeticity of the lattice. Okay, maybe, but even in the last statement, like in Breuil's statement, there is no number theory there. It's just about linear groups over arbitrary fields. So this is, I think this is it's quite striking that this statement plays a role, and it shows that, this Lehmer conjecture, there's business there. Like it's something, something happens. So yeah, unfortunately, I think it's far from our full understanding. I don't think we'll see a proof in our lifetime, but nevertheless, I think it's an interesting thing to study. And I think I'll stop here. So I put some references down if you care. And I'm open to answer any questions you may have.
All right. Thank you, Francois. That was a very interesting talk. So do we have any questions from the audience? Seems like there are not any, or maybe people are shy because they know that it's being recorded. So let's thank Francois again. And
thank you.
We can stop recording. All right, thanks.